Chapter 7 covers the reactions of alkynes. So we've looked at the reactions of alkenes and how they react with reagents such as HBr, acid-catalyzed hydration, and hydroboration oxidation. And now we're going to look at another molecule with pi bonds that will be nucleophilic alkynes. And we're going to look at some of the same reagents. You should expect the same reactivity, but remember, the difference between alkenes and alkynes is that alkynes have 2 pi bonds instead of 1, so potentially twice the reactivity. Okay, some naturally occurring alkynes include capillin, ichthyotherol, a convulsant, and an enediene, shown here, which is a class of anti-cancer drug. So there are several anti-cancer drugs, and the variation between the drugs is variation in the 5R groups around the enediene. Some synthetic alkynes that are not naturally occurring include the parasalmide analgesic, synovial, and pargylene, the antihypertensive. Okay. What? This is, I don't know why that's there. I'll erase it. That's going back to chapter 4 and molecules. This would be a meso compound. But we don't need that for this chapter. Not right now anyways. Okay. Of course, when we've started a new molecule type, so we're going to have to look at nomenclature of alkynes. In this case, when we go from alkane with no single bonds to alkenes, we change the suffix to reflect that a double bond is going to have the suffix of -ene, while a triple bond is going to have the suffix of -ine. So we're going to ignore common names. Common names are not something we're going to worry about, and we're going to focus on our systematic names. So 2-carbon alkyne, the smallest possible alkyne is ethyne. Whenever we name an alkyne, you want to choose the longest chain containing the alkyne, and then put the alkyne at the lowest possible carbon number. So 1-butyne, and the carbon number of the alkyne is indicating where the triple bond starts. Our examples here are 1-butyne, 2-pentyne, 5 carbons with the alkyne bond, the triple bond between carbon 2 and 3, and then also 4-methyl-2-hexyne, and that is showing that the longest chain is going up. 1, 2, 3, 4, 5, 6. So that's 6 carbons with an alkyne bond between carbon 2 and 3, and a methyl group at carbon 4, 4-methyl-2-hexyne. The chain is numbered in the direction that gives the -ine suffix the lowest possible number. Continuing, if the numbering of the alkyne bond is the same in both directions, so if I count from the left, I get 1, 2, 3, 4 for the alkyne. If I count from the right, we get 1, 2, 3, 4 for the alkyne. Then we are going to choose the numbering direction that gives the substituents, or the branches, the lowest possible number. because the triple bond is the same in either direction. It doesn't matter for the triple bond. So then we consider branches. So we would start numbering the molecule at the left, from the left to the right, because the chloro and the bromine would be on carbons 2 and 3 if we number from the left to the right, but they would be on 6 and 7 if we were to number from the right to the left. And 2 and 3 are less than 6 and 7, so we're going to number from left to right. Then we can look at the other example here. We have that the alkyne is at carbon 3, 1, 2, 3, whether I count from the left, 1, 2, 3, or the right. And then for numbering, I could have substituents either at carbon 1 or carbon 6, and carbon 2 or carbon 5. So we are comparing 1 and 5 to 2 and 6. And 1 and 5 is less than 2 and 6. And so we're going to have the bromine bonded at carbon 1 and the methyl bonded at carbon 5, because that gives lower overall numbering. So this would then be 1 bromo, carbon 1, bromine, 5 methyl, carbon 5, methyl, 3 hexyne, hex meaning a 6 carbon chain, and 3 yne being the position of the triple bond in that 6 carbon chain. Okay, if we have 2 of the same functional group, we're going to have, we're going to call it a di-functional group. And so if we have a diene, 2 double bonds, ene is a double bond and di is 2 double bonds. So that should be fine. And then if we have another diene in the middle here, but the chain is longer. So this is 6 carbons. We have a methyl group at carbon 2, and the double bond carbons are carbon 1 and 4. So we have a double bond between 1 and 2, and a double bond between 4 and 5. So we're going to state 1 and 4 to indicate where the double bonds begin, and then the number of carbons in the main chain, hex, and then the number of double bonds, di, and then the fact that they are double bonds, ene. On the last example, we have a 2 triple bond molecule with 1, 2, 3, 4, 5, 6, 7 carbons total. And if we're numbering our triple bonds to have the lowest possible numbering, then we would number from the right to the left, so that carbon 1 is our first triple bond carbon. Our first triple bond is between carbon 1 and 2. And our second triple bond is between carbons 4 and 5. Our methyl group is at carbon 6. And so this is I always start with the suffix first, which means that I'm going to write down how many carbons in the main chain, hept, and then how many triple bonds I have, and the fact that it is a triple bond, yne. So we have a heptadiene. Then I'm going to put down what carbons the ynes are at, carbon 1 and carbon 4. And then I'll name the substituents, or the branches from the main chain. So that would be 6-methyl is our only branch. And that gives us our full and complete name for this molecule, 6-methyl 1,4-heptadiene. The difference between or a double bond, and what if we have both a double bond and a triple bond in our molecule? If we have both a double bond and a triple bond in our molecule, we will have both -ene and -ine in our suffix. We're going to include both -ene and -ine in our suffix. So the way that we're going to do that is that we're going to number the chain so that the triple bond has the lowest possible number. So either the triple bond or the double bond could have the lowest possible number, as long as the overall numbering for both functional groups is the lowest possible. So the chain is numbered in the direction that produces the lowest number in the name, whether that means you start with the carbon closest to the triple bond or the carbon closest to the double bond. So for the first one, we have numbering from the right towards the left. The triple bond is at between carbon 1 and 2. We have a total of 7 carbons in the chain, and we have a double bond between carbon 5 and 6. And the way that we're going to account for having both a triple bond and a double bond is to give the number of the, write the suffix first, so -ine. Then immediately preceding the suffix, put the number of the carbon that the alkyne is at, 1. And then preceding the number that the alkyne is at, place the total number of carbons, including the -ene suffix to reflect that it's an alkene. So 7 carbons, hept, alkene, En. So the En is for the double bond. But we also have to know where the double bond is located. And so before the hept, indicating the 7 carbons, put the carbon number of the alkene, 5. So then this molecule is 5 hept and 1 ine. At the top right, we have another molecule that is the 7 carbon chain, but in this case, the lowest numbering is obtained by having the double bond between carbon 1 and 2 and the triple bond between carbon 5 and 6. Same methodology, write the suffix -ine. Before the -ine suffix, write the carbon number for the triple bond, 5. Before the 5, write the total number of carbons in the main chain and the En indicating the double bond. So there are 7 carbons, so it's a heptene. And then before the indication that there are 7 carbons, put the number for the double bond, indicated by the En after hept. So the double bond is at carbon 1, so this is 1 heptene, 5 ine. And then we have another chain, okay? So we want the longest chain that contains both functional groups. The longest chain total is 7 carbons, but the longest chain, 7 or 8 carbons, but the longest chain containing both functional groups is 6 carbons. So the group at carbon 3 as labeled is going to be a branch. So the longest chain containing both functional groups is 6 carbons, and then we're going to call the group at carbon 3 a branch. And that branch has 4 carbons, so it is a butyl branch. So now, if I start with my suffix, I have -ine. I should probably give myself more room. So if I start at the end, I have -ine. the ine is located at carbon 4. Before the ine, I have my alkene, En. How many total carbons in the main chain? Hex. Hexene, 4-ine. The number for the double bond goes before the hex, and that's carbon 1. And then before the number for the double bond, I'm going to put the chain, the branches off, the substituents of the main chain. So that's where I would put the butyl. But then I need to say, where is the butyl located? It's located at carbon 3, so we begin with 3. And that's just my thought process, is to work from the end to the beginning. And that gives me 3 butyl, 1 hexane, 4-ine. Double and triple bonds are tied. So what if the numbering will give us that 2 and 4 are the lowest possible numbers from either direction? Are we going to put the triple bond at 2 and the double bond at 4, or the double bond at 2 and the triple bond at 4? So those are, let's write out those options. So options. What is correct? 2-ene, 4-ine, or 4-ene, 2-ine. And the answer is that we are going to give the double bond if we have the same set of numbers, 2, 4, and the only thing that changes is whether the 2 is for the ene or for the ine, then we're always going to put the double bond at the lowest possible number. So we're going to start numbering so that the double bond has a lower number than the alkyne. So then that would mean that my suffix, if the double bond has the lowest possible number, would be 4-ine, because 4 is the higher number. I'm giving it to the alkyne. And then I have a 6-carbon chain, so before my En, indicating the double bond, I'm going to put hex to reflect 6 carbons, and before the hex, I'm going to put the carbon number of the alkene, carbon 2, so that this is 2-hexane, 4-ine. And then you can see on the second example at the right, we numbered whether we, on the right, the options are that we can have 1-ene, 5-ine, or 5-ene, 1-ine. And the answer is that the double bond gets the lower number. So 1-ene, 5-ine. And then from there, we just need to know total number of carbons, 6, and we'll be able to name our molecule. We're going to put the number for the double bond at the beginning, 1-hexane. So we put the 1 for where the double bond is located, the hex for the total number of carbons in the chain, and the ene to indicate the double bond. Then you put the number for the triple bond, 5, and the suffix indicating the triple bond, ine. Okay. Priorities of functional group suffixes. So the highest priority that we have looked at to date is the ketone, which would have a suffix of -one. We actually haven't named any ketones yet, I don't think. We have named alcohols, and the suffix for the alcohol is -ol. The suffix for the amine is amine. The suffix for the alkene is En, and the suffix for the alkyne is -ine. The double bond is given priority over the triple bond only when there is a tie between possible numbering. So what this means is that if I have a double bond O and an alcohol, and my longest possible chain containing both functional group is 5 carbons, because the double bond O has a higher priority than the OH, then the double bond O gets the lowest possible number. And the double bond O is the suffix, so this would be an -one. It would be a pentanone because it's a 5-carbon ketone. And then we would say that at carbon 3, we have a hydroxy group. So the alcohol group, because it's not the main priority, is not the suffix. It ends up being a prefix, and we call it 3-hydroxypentanone. Actually, we need the number for the ketone, 3-hydroxy-2-pentanone. We have to indicate what carbon number the double bond O is at. 3-hydroxy-2-pentanone. Okay? So all carbonyl molecules, all molecules containing a C double bond O are going to be a higher priority than alcohol. And there are a lot of C double bond O molecules. We have aldehydes, ketones, carboxylic acids, esters, amides. All of these molecules contain a C double bond O group or a carbonyl group, and they're all higher priority than alcohol. But we'll look at those, naming those molecules later as we come across making them. Okay, so OH and NH2 have a higher priority than the double bond and the triple bond. But the double bond and the triple bond will never go to being complete prefixes. What we do instead is have 2 suffixes, and we put the higher priority suffix at the very end, and the lower priority suffix indicating the double or triple bond at the end of how many carbons there are in the main chain. Okay, so for example, let's parse this out. So at the very end, you have the suffix for the higher priority functional group and the carbon number of that group. So carbon number, higher priority functional group, and suffix, higher priority group. Then next, we have the total number of carbons in the chain, in the main chain, plus or and suffix for lower priority group. And then we only do suffix for lower priority group when we're talking about double and triple bonds. So we wouldn't call something an amine all. We only do it for alkenes and alkynes. Suffix for lower priority. Ene or ine. And then at the very front, we have the carbon number for the ene or ine location. Ooh, ine. I put yen instead of ine. Did you guys see that? Y-N-E. Location. Okay, and these rules apply to both chain molecules and cyclic molecules. Okay, so let's look at some of the other names. At the very end, the higher priority functional group, the alcohol. The higher priority functional group is always given the lowest possible number. So it's at carbon 1. So we have the number indicating where the higher priority group is located. Then we have total number of carbons in the main chain and the suffix for the lower priority group, the alkene. So it's a pentene, 5 carbons with a double bond. Then before that, the location of the lower priority group, the double bond at carbon 3. And so that takes care of the main chain. Then we have to look at branches and name the branches. And that goes in the front for methyl. So at carbon 4, we have a methyl group. Okay? So amines also have higher priority than alkenes. And we're going to give our higher priority functional group the lowest possible numbering. So then this amine is at carbon 2. So at the very end, I'm going to put 2 amine to indicate that that's the highest priority and the number of the carbon that it's at. Then the total number of carbons in the chain and the fact that it contains double bond, heptene, and the number of the carbon at which the double bond exists, carbon 6. Okay, so you should have that down now on how that pretty much goes. We have a 6 carbon chain with an alcohol at carbon 2 and alkene at carbon 3. So lower priority number group at front 3, total number of carbons in the chain hex, lower priority functional group ene, number of higher priority functional group 2, identity of higher priority functional group all. Okay, for a ring that contains both an alcohol and a pi bond and a methyl group, we're going to give the lowest possible number to the alcohol. That's carbon 1, because it's the higher priority. The alkene has to have the next number. So the alkene is between carbons 2 and 3. And that would mean that our methyl group is at carbon 6. So for naming this, the number, I would put the branch first, 6-methyl, then the number of the carbon for the lower priority functional group 2, then how the identity of the longest chain of carbons, cyclohex, the fact that it contains a double bond, ene. So we're at 6-methyl 2-cyclohexene, and then we don't have to put the number for the higher priority functional group because it's understood that it's at carbon 1. So as long as you know the rule that it's at carbon 1, you don't have to state that it's at carbon 1. So then we can just end with all. We have the same basic rules for the 3-cyclohexanamine. It's understood that the amine is at carbon 1, so you can put a 1 there. If you number from there to give the double bond the lowest possible numbering, we're going to have to go counterclockwise, and that will give us the double bond at carbon 3. So we have 3-cyclohexene, so cyclic 6-membered ring with a double bond at carbon 3, and then amine, and it's understood that the amine is at carbon 1. The structure of alkynes. We looked at this in chapter 1. Alkynes are 2 sp hybridized carbons involved in a triple bond that are also bonded to hydrogens. Sp carbons have a bond angle of 180 degrees, so it's linear geometry. The 2 pi bonds are not in the same plane. They are perpendicular to one another. So we have purple parallel p orbitals for one pi bond and blue parallel p orbitals for the other pi bond. The electron density for the alkyne is highest at the location of the triple bond. So if you look at the electrostatic potential map, you can see that the red, or the highest electron density, is focused in the area where you would find the 2 pi bonds.